Okay, let's start. So let's recap as usual what we have taken last time. So we saw how to solve a circuit. Solve a circuit means to get the current and also the voltage, okay? Using basically nonlinear equations, because the equations that relates the current to the voltage of the diode device, the junction, is actually nonlinear. So we have to do that, okay? Although other, other elements are linear, but this guy is not linear, like the resistor. And we saw that it's accurate, but it needs the programming and the iterative solutions, for example, to get it fast, So that's why we will not, do that anymore. I mean, solving problems using nonlinear equations. Then we see another approach, which is, it's also accurate, by the way, which is, you assume, from the, characteristic of the diode, you can assume the operating point, for example, or the operating region. And for each region, there are some characteristics, especially in reverse bias. Okay. So we think about the givens. For example, if the diode is forward, if the diode is reverse, then based on the givens again, we make some assumption. Then you approve or disapprove it based on the outputs. For example, if you assume that the diode is forward and you find that the current is negative, then you are wrong. Your assumption is wrong. Then you should make another assumption. And the opposite is correct. If you assume the diode is reverse and you find that the current is positive, then your assumption is also incorrect. And you should assume another assumption. Okay. We also studied this example here. Oh, sorry, something went wrong with. Yes. We also see this example here, okay, in which we studied the situations or the operating point of these two diodes, diode 1 and diode 2, in two givens or two conditions or under two input voltages. We found that at V input equal to 90 volts, when V input is equal to 90 volt, D1 was in deep reverse, but not breakdown. And D2 was just reverse. Basically, we find that D1 is working somewhere here. And D2 was working somewhere here in that region. Okay. And that's basically, very logic, because D2 can have up to -2, I know, or -2, I'm sorry, -2 microamps. This is ID2, VD2, VD1, ID1. But ID1 in reverse can have up to -1 microamps. So D2 can afford up to 2 as the magnitude, but D1 can afford only up to 1 microamps. But they are in series. They have the same current. So one of them must comply to the conditions of the other one. So it's like if you have, you know, a grown-up, a father, for example, is walking beside his son. That, you know, this son just, you know how to walk. He's just maybe 2 years old or something. So the father, of course, is an adult. He can run, you know, he can move slow, he can move fast. Okay, but this guy that just, you know, learn how to walk, he only, you know, barely walking. So this guy can have, you know, can run, for example, can walk, but this guy can just barely walk. So for them to walk with each other in the street, for example, you know, the father, D2 in our example, must comply with the conditions of his son, the child, which just, you know, barely walk. So the speed of both should be restricted to the maximum of the child here, the lower speed. So the two currents here, D2 can have up to minus 2 microamps. D1 can only have up to minus 1 microamps. So D2 must comply to the conditions of D1, I'm sorry. And, you know, he can have minus 1 microamp, okay, but D2 cannot have minus 2 microamps. When we put V input equal to 110, okay, we increase this, and when we working at V input, we found that the voltage of VD1 was around minus 89.9 volts. Okay, and we found that the voltage of V1 was very small, minus 18 millivolt. Then we increase V input by 20 volts. And actually, the breakdown here actually happens at the same voltage for both, minus 100. And V1 needs only minus 10 volts, and he can go directly to the breakdown. So that was a reasonable assumption, and this is the assumption that we, you know, that we assume that VD1 will go to the breakdown, while VD2, which, you know, has only minus 80 millivolt, needs 100 more to reach the breakdown. So we assume it's just in deep reverse, but not breakdown, somewhere here, and that works. This assumption was correct, and the other assumption was wrong. Okay, good. So let's now go to another example that just based on this example. So this is exactly the same example that we just described, but we have two additional resistors, R1 and R2, but both has the same value of 10 mega ohms. 10 multiplied by 10 to the power 6 ohms. Very high resistors. Okay. Again, let's examine how we solve this as exact solution. So again, the requirement, or yes, we have four unknowns: ID1, ID2, VD1, and VD2. And again, these directions are very important, because based on this direction we make KVL and KCL. So you must assume them properly. Okay, so the exact solution we need 4 equations. So we have basically the equations for the currents and the voltage of the diode. So ID1, I naught 1, E VD1, VT minus 1. ID2, let's call this number 1. ID2 equal to I naught 2, E VD2, VD minus also 1. So far we have 2 equations and 4 unknowns. Remember, VT is known at 300 degree Kelvin if the temperature is not mentioned, so you can assume it's 300 kelvins. and VT will be 26 millivolts. And I note 1 and I note 2 are given in the example, 1 micro and 2 microns. But still we need 2 more equations. We have still the KVL. So we can, let's have another color here. We can have this loop here. And based on that loop, we can have V input plus VD1 plus VD2 equal to 0. 3 equations in 4 unknowns. Now, someone of you can tell me where is the 4th equation will come from? The 4th equation in the previous example, without these resistors, was that ID1 equal to ID2 equal to I, for example, or whatever. But how about with these new resistors? What should be the 4th equation? Any volunteer? Should be very easy, guys. You can write or chat. Okay, nobody is. Okay, that's fine. I'll do that. It's also KCL. Okay. So we have here a node. This node here. This node here. Okay. And this node has 4 currents going out and in to it. Okay. So from KCL, we can say that, let's see who is output and he is input at that point. So let's assume that we have 2 current in R1 and R2. So let's assume the current in R1 is called I1 and flowing down. And the current in R2 is also flowing down and called I2. So at that node here, the inlet currents, the currents that going into the node, should be equal to the currents that going out of the node. What's going into the node? ID2 and also I1. What's going out of the node? ID1 and I2. But we added here 2 new unknowns, I1 and I2. So we need 2 more equations. Well, actually, it's not that complicated because the voltage on R1, let's assume this is VR1, is actually from this small loop here, very small loop. The voltage VR1 is actually equal to minus VD1. And VR1 is equal to I1 multiplied by R1. So I1 is actually VD1 using the same VD multiplied by R, I2 multiplied by R2. So I2 is actually a function of VD2. So this equation here, the KCL, can be written in that way. ID2 plus I1. I1 is equal to minus VD1 over R1 equal I2 plus, I'm sorry, ID1 plus I2, but I2 is equal to, from this equation here, I2 is equal to VD minus VD2 over R2. So VD2 over R2. I remove the plus. So this is our fourth equation, and that's it. Okay, so we have 4 equations, then go to MATLAB or whatever, make it, you know, by hand. It will take time, but anyways, and you can solve it. But we will not do that because we can do it in a simpler way using the assumptions. You know, you assume some assumption and, you know, you approve it or disapprove it. So solution 2, it's also exact, but more smarter, we can say. So in that case here, let's call it B, smarter way. So in the smarter way, we're gonna look first about the condition of the VD1 and VD2. VD1 and VD2 is actually, and compare it to the V input, they both reverse biased, because the positive terminal of the V input is closer to the negative terminal of both, okay? And the negative terminal of V input is closer to the positive terminal of both. I mean the B side of the diodes. So we know that D1 and D2 are reverse. But are they in series like the previous example? No, they are not in series. If they are in series, we have a trouble. One of them can be in deep reverse, the other cannot. Maybe yes, or maybe not. If they have different I note, no. One of them will be in deep reverse if the input is large, but the other will be not in deep reverse based on its I note. But now they are not in series anymore. So we can assume here that D1, so we'll assume, so let's write it clearly here, because this is an assumption that must be proved positive or negative, or I'm sorry, right or wrong. So the assumption here, that D1 and D2 both are deep reverse, but not breakdown. And this is, by the way, at V input equal to 90 volt. Okay. And of course, in the exact solution, you should, you know, solve these set of equations 2 times, one at 90 and one at 110, which make it more complicated. But why I didn't assume in the beginning or now that they are not breakdown? Basically, because the breakdown voltage for any one of them is 100. Okay. So, but the input is just 90. So from where any one of them can afford the 100? They are dependent on the input. So they don't have any other source to provide this extra 10 volts. Okay. So it's smarter here, based on the givens that the V input is just 90, is to assume, yes, they are reversed because they are reversely connected to the input, but not breakdown because the input itself is less than V breakdown, which is 100. Good. So let's approve or disapprove this assumption. Okay. Since D1 and D2 are in deep reverse, then we can assume that ID1 equal to minus I naught 1 and the ID2 is equal to minus I naught 2. Two of the unknowns are solved now in a very easy way. Okay. Now, how are we gonna get VD1 and VD2? Basically, look at the circuit. You will find very interesting stuff here. First, now we have two unknowns, video and video. So we need only two equations. Actually, we write the equations. Okay, we don't need, to do them again. So we have this equation that VD1 plus VD2 plus V input is equal to 0. This is equation 1. And V input here is 90. So it's equation in just the two unknowns. And the other equation is actually here, number 4. That ID2, which is known now, minus VD1 over R1 equal to ID1, which is also known, minus I01, minus VD2 over R2. This will be equation number 2. So we have two equations and two unknowns. And this guy again is minus I02. This guy is minus I01. R1 is 10 mega ohms. R2 is 10 mega ohms. So there are two equations and two unknowns. We can solve them very simply. And by the way, they are linear. Okay, so we avoided all the nonlinear equations, which is the diode equation, diode 1 equation, and diode 2 equation. And we found that from 1 and 2, if you solve them linearly, very easy steps, you will find that VD1 equal to minus 50 volts, VD2 equal to minus 40 volts. And you kind of check that VD1 plus VD2 is actually equal to minus 90. So KVL will be, satisfied. This equation, that V input, which is 90 minus 40 minus 50 equal to 0. So we are on the right track. Let's have another check. We said that these guys are in deep reverse, right? So, and based on that, we said that ID1 is equal to minus I01. So let's, go back to the equation of ID1 and prove that again. So ID1 is equal to I01 e to the power VD1 over VT minus 1 equal I01 exponential, let it write as exponential, that's fine. VD1 is minus 50 over 26 millivolts minus 1. If you do that on calculator, this will be 0. So this is minus I01. And you can do the same for ID2 equal ID I02 exponential minus 40, which is VD2 over 26 millivolts minus 1. Again, this guy is 0, so this will be minus I02. So we are on the right way, and this is the correct assumption. Somebody would say, no, I think, we could assume, of course, any other assumption will be wrong. But let's, assume some wrong assumption, okay? And for you, is it, for example, if this is an example or homework, that's fine. So you just solve with the mystery, okay? But for us in the lecture now, I want to just, make you more sure about what you have done or what you have solved. So let's assume an incorrect assumption, something that is not logic even, and disapprove it. So we said that they are not breakdown, right? So let's assume one of them or even two, both of them are breakdown. So here it is complete. So let's here assume that, for example, D1 is breakdown and D2, so reverse, or yeah, breakdown, that's fine. Okay, that's good. So if, and D2 is just, for example, in deep reverse, but not breakdown. Let's assume, by the way, this will be a correct maybe for, yeah, this was correct for the other example in number 2 when V input is equal to 110. But anyway, let's disapprove this. If we assume D1 is in a breakdown, then VD1 should be minus V breakdown, so minus 100. Okay. If VD2 is deep reverse but not breakdown, that means that VD2 is less than V breakdown as a magnitude, less than 100. Okay, let's see. Let's see if this is right or wrong. So we have V input plus VD1 plus VD2 equal to 0. V input is 90 plus VD1 minus 100 plus VD2 equal to 0. So VD2 is equal plus 10 volts. Plus 10 volts. That's a positive voltage. That means D2 is not, or is not reverse, basically. So your solution, your assumption here is not correct because you assumed in the beginning, and you are sure of that, by the way, that D2 is actually was reverse. But and if a diode is in reverse, its voltage must be negative. But you just, based on this wrong assumption that D2 is reverse, which is wrong. So that's wrong. Okay. Maybe somebody will say, and of course you can do the opposite. If you assume D2 is reverse, then its voltage will be minus 100, and D1 is deep reverse but not breakdown. You will get the same stuff. Let's assume another bad example or bad assumption that both D1 and D2 in reverse. Okay. Which is basically wrong, because if both in reverse, that means both of them will have 100 volt. So the input itself must be more than or equal to 200, which is not the case, even for A or B, 90 volt or 110 volt. But let's do that. So VD1 equal to minus 100 volts, VD2 equal to minus 100 volts. V input plus VD1 plus VD2 should be equal to 0. Let's see. V input is 90 minus 100 is actually equal to minus 110 volts. That's not equal to 0, so this is a wrong assumption. And so on and so forth. You can assume whatever you like. You will find some discrepancy in the outputs. That means the assumption is incorrect. Good. Yeah, just one quick note here. So this guy here, let's write it red, should be less than VBD and, as a magnitude larger than 0, or VD2 as, just to make you more sure, VD2 as just as a value, not absolute value, should be larger than or greater than minus 100 and less than 0, because it's reverse. So we found it, equal to positive 10, and positive 10 is not in that range, so it's incorrect again. Okay. Okay. One thing from the previous A is that D1 and D2, remember in the previous example number 2, one of them restricts the other. So one of them becoming deep reverse, the other continue in deep reverse, which is D1, but D2 was not in deep reverse. Okay, and the addition of these two resistors prevent that from happening, prevent this dependency between the two diodes. Okay. In the previous example, again, when we increase the voltage to 110, D1 goes to the breakdown, but this will not happen here. Why? Basically because from A, let's write this in red, from A, when V input is equal to 90, we found that VD1 is equal to minus 50 volts, VD2 is equal to minus 40 volts. Just 1 minute, guys. I have here 1 minute and I will come back. Okay, just hold in the meeting. It's okay now, it's okay. Okay, so let's continue that. Yeah, working from home is not. Okay, so with V input is equal to 90, we found that VD1 is equal to minus 50 and VD2 is equal to minus 40. And remember, V breakdown is minus 100. So VD1 needs 50 volt, another 50 volt as a magnitude again, to reach this breakdown. And VD2 needs 60 volt to reach. Also, the input here has just increased by 20 volts from 90 to 110. So even if this extra 20 volt goes to D1, which has larger value as a magnitude again, it would be 70, right? Still away from the breakdown. So it's not logical at all to assume that D1 or D2 in breakdown. This will be a wrong assumption. Okay? So the correct assumption here is to assume again that VD1 is in deep reverse, VD1, I'm sorry, D1. D1 and D2 both in deep reverse but not breakdown. And that's again will lead us to the same conclusions, but different values because V input has changed. So I D1 will be equal to minus I naught 1. I D2 is equal to minus I naught 2. Okay. And still we have from KVL V input plus VD1. Same equations. Just one number will be changed. VD2 is equal to 0. And this is equation number 1. And we have another equation which is I. This is I'm sorry, this is I1. This is I2 from this node here. So I1 minus VD1 over R1, I'm sorry, 2 and 2, yes, equal I2 minus VD1 over R2. This is minus, this is equation number 2. From 1 and 2, we find very interesting, result that VD1 is actually equal to minus 60 volt. What? I'm sorry. What will happen? Yes, minus 10. That's right. Minus 60 volt, and VD2 is equal to minus 50 volts. Both of them has increased by 10 volts. So when we increase the voltage, okay, what happens is just, the extra voltage goes equally or divided equally between the two diodes. Each one has take just 10 volt extra out of 20. Okay. And you can do the same checks again. ID1 you will find ID1 is equal to minus I naught 1, and you will find that ID2 is equal to ID2. It's very simple, right? We didn't even do anything. We just have the same equations, okay, from A, and we just plug the new value for V input. That's it. Let's assume incorrect. Oops. Some incorrect assumption again, just for your, information. So assume, let's do it in red to be compatible with our, assume D1 goes to reverse, or I'm sorry, goes to breakdown, for example. Okay, so VD1 equal to minus 100. Okay, so V input plus VD1 plus VD2, this should be equal to 0, but let's see what will happen. V input is 10, VD1 minus 100, VD2 we don't know. Okay, we assume it's just reverse, so D2 is just a deep reverse but not breakdown. So VD2 here is equal to good. So because VD2 is equal to minus 10, okay? So it looks like we are really in deep reverse but not breakdown. But some things that I missed here is that since we are in breakdown, so I note as a magnitude, I note ID1 as a magnitude should be larger than I note 1. Okay, that's the thing that I missed. So we know that this is VD1, ID1, and this is minus 100. We know that when D1 goes for our D2 goes to the breakdown, the voltage will be constant at the breakdown, but the value of the current as a magnitude should be larger than I naught 1, the reverse saturation current. And that's actually not correct here, as we will see right now. We continue with the same equations again, okay? And calculate ID1 and ID2. So let's see ID1. ID1, yes. If you did this, if you calculate ID1 based on these, calculations, you will find that ID1 is equal to 7 plus 7 microamperes. Okay, so let's look at the plot here, the graph here. So ID1 should be minus, should be negative, because we are working in the reverse bias. Although based on the, when you solve the equations, you will find it's equal to plus 7 microamps. Whatever the value is, since it's a plus, then it's incorrect, because it should be in a minus value and as a magnitude larger than I naught 1 to be working really in that region here. So that's what's prove it wrong. Okay, so that's a good example, because from the beginning we found that VD1 is equal, VD2 is equal to minus 10, looks reasonable because we assumed it's in deep reverse, not breakdown. But then when we calculated I1 and I2, and I should put the numbers for your reference, if you calculate, you will find that I1, which by the way is equal to minus VD1 over R1, equal to minus 10 microamps, minus 10, yes, microamperes, I2, I'm sorry, equal to minus 1 microamps. Then if you continue in the calculations and calculate the current, and here ID2 is known, equal to minus I naught 2. So you have only one unknown here. So if you calculated ID1, it will be, it will not be here. It will be somewhere positive here, which is, wrong, because it should be reverse bias. Okay. So that's basically the why this is the only correct assumption, so is the first one, and this is incorrect. Any other assumption will be incorrect. Okay, so let's go to another example. Yeah. we just, you know, in this previous two examples, example 2 and example 3, we saw that the diode can go in reverse and can go even in, I'm sorry, can go in this breakdown region, okay, based on the input voltage. If the input voltage is large enough, larger than or greater than the breakdown voltage, the diode can go into the breakdown. Okay. But usually for normal rectifying diodes, these diodes that I'm explaining right now and putting in examples called rectifying diodes. And rectifiers are one of the examples that we're gonna see maybe next lecture for diodes. Okay. In the next lecture is the one next it, maybe next Monday, next Tuesday maximum. So one diode in particular called Zener breakdown. Zener diodes, okay, are, you know, designed to work in breakdown, but at very lower voltages than, you know, normal rectifying diodes, the ones that I usually, you know, that we usually see, which have, you know, very high breakdown voltages like 100, you know, 1000 maybe. But Zener diodes are diodes that have the following something similar to the following characteristics. Let's call that V Zener, I Zener. And this is, let's call it VD, and yes, VD, because they usually calls so this is VD, just it's a diode, okay, but it's a breakdown usually called V Zener, okay. Yeah, V Zener is a breakdown voltage for Zener diode. And based on the Zener diode, you have, you may find this diode and know what's actually it's Zener, it's breakdown voltage. But you will see that usually this breakdown voltage is very small, maybe less than 20 volts. And tomorrow in our lab, we're gonna see the Zener diode and some of its characteristics. Okay. So I'm just, you know, bringing that to your attention here in that lecture here. Okay. Because we're gonna see it in tomorrow in the lab, okay, and we're gonna see also one of its applications as well. So Zener usually small than the breakdown voltages of rectifying diodes. Okay, those has usually in hundreds. This is maybe less than 20 or something. Usually very, very small. Okay. And again, if the Zener is working in this breakdown region here, its voltage will be equal to V Zener, and its current here, the current ID as a magnitude must be larger than I naught, or as a value ID as a value less than minus I naught. So if, for example, if I naught is minus 1 milliamps, ID should be, for example, minus 2 milliamps or lower. Okay. So, and the breakdown mechanism here is not the ones that I explained to you when I explained why we have breakdown in diodes in general. Okay. So the one that I explained is called avalanche breakdown, okay, in which you have a very big reverse voltage. So you have a very big reverse electric field. So that will, you know, attract some of the electrons from the atoms, and they will go with very fast speed, hitting other atoms. These other atoms that were hit with these electrons will, you know, emit other electrons, and so on and so forth. Okay. This one has a relatively different mechanism, okay, at which can happen at even lower voltages. So we need only very low, compared to the first one, very low reverse breakdown voltage. Okay. So let's have another example. I just bring it to your attention because we will take it tomorrow in the lab. Okay. But we will take applications for it maybe after 3 lectures or something. So let's have another example. Okay. This one is similar to example 3 and 2, especially example 2. Yeah. Now, in example 2, we have 2 diodes. They were in the same direction. Okay, so in example 2, we have the 2 diodes like this. Right? And both were reverse bias. Now, in that example, and both were series. Now, we have 2 series diodes, 2 diodes connected in series, but they are connected back to back. Okay, so this is the B of the, you know, this is the B of the first one, and this is the N, and then this is the B, this is the N. In that situation here, both were reverse bias, but the problem where they are not in the same region in reverse bias. But now here, D1 is reverse because its N is closer to the positive terminal. Its B is closer to the negative terminal. D2 is actually forward because its negative is closer to the negative terminal, and its B is closer to the positive terminal. So D1 here is reverse. D2 is forward. And the input is equal to 5 volts. 5 volts. In A, it says that if the breakdown voltage of each diode, they are identical, by the way, and this is very important. When it says they are identical, that means I naught is equal to I naught. I naught D1 of D1 is equal to I naught of D2. And the same breakdown voltage, since they are identical. Okay. So the characteristics, the geometry, and everything else is doping, everything is identical. Okay. Good. Now in A, the breakdown is larger than 5 volts, which is larger than the V input. So based on our experience now, we know that D1 will not go to breakdown, or we will assume that. Of course, we will assume our assumption will be correct, but you know, based on common sense. But we will assume that, and we will see afterwards, based on the numbers that we get, that this is a correct assumption. Okay. So let's assume also, now we have two diodes. One is forward and one is reverse. Okay. And we know that D1 is not reverse. I'm sorry, it's not breakdown. I'm sorry. So its current should be maximum minus I naught 1 as a magnitude. for I naught 1. Very small current. Although VD2, which is forward, can, you know, have very large currents. So again, we will go back to the first analogy that we have. We have now two diodes connected in series. So they will be dependent on each other because they must have the same current. So again, if we go back to the same, you know, analogy, if you have a father with a child, okay, the father must be restricted to the child's speed when they walk together. And this guy will be the reverse, the diode in reverse bias, and this guy will be the diode in forward bias, which is D2 in that example. Since D1 is not breakdown. Okay, so let's assume that D1 is in deep reverse. I'll write it here. Deep reverse, not breakdown. So ID1 is equal to minus I naught. And we will stick to the same directions of current that we should always do with diodes. And with diodes, always the voltage direction from the N to the B, N to the B, and always the current direction from B to N. So this is ID1, and this is ID2. And we can have, you know, two currents in the same, but they will be, of course, with negative, with opposite polarity, negative or positive. So from this circuit here, ID1, from our assumption of the currents, ID1 is equal to minus ID2. They both have the same value, but since we are assuming them in different directions, one is counterclockwise and the other is clockwise. So ID1 is equal to minus ID2. But ID1 now is equal to minus I naught. So ID2 is equal to minus minus will be positive, so positive I naught. So far we are in a good shape because D1 is in deep reverse, so its current is minus I naught and it must be minus. D2 is forward, so its current must be positive. And its voltage as well. Let's calculate VD2. We know that ID2 is equal to I naught exponential VD2 VT minus 1. ID2 is equal to I naught. So here is I naught. This will go with this. So 1 equal to exponential VD2 VT minus 1. So exponential VD2 VT is equal to 2. So VD2 is equal to VT ln 2, which is log to the power to natural number of E, which I call it ln. I don't like using log because it confuses me. Okay, so this is very easy to do. Okay, and based on that, VD2 will be equal to how much? 18 millivolts. Very small one, and I will say why it's very small. And it must be very small. Now, now let's calculate VD1. Now, here we have a loop. So V input plus VD1 minus VD2 equal to 0. V input is 5. VD1 is unknown. V2 is 18 millivolts equal to 0. So VD1 is equal to minus 498 volt. Before we continue, it's minus. Okay. And we were expecting, since D1 is reverse, we know it should have a negative current, negative voltage. VD1 is positive. And that's correct because we know that it should have positive current and positive voltage. Now let's do some checks to see if our assumption is right or wrong. Actually, it's right. So the basic check here is that we said that since VD2, or I'm sorry, D1 is in deep reverse, its current is minus I naught. Okay, good. ID1, so this is a check, equal to I naught, which we don't know, by the way. We don't need to know it, since the required was only the VD1 and VD2. I naught exponential VD1, this is I'm sorry, ID1, over VT minus 1. VT is minus 498. This guy is 26 millivolts. So this is like, you know, e to the power minus infinity. So this will be 0. So this is minus I naught, which proves our assumption is correct. And we just finished. Okay. Any other assumption will be incorrect. Okay, I'll do that for you. Just assume anything you want rather than these assumptions, and you will find it wrong. Okay, that's good. Okay, we have 10 minutes. In particular, if you want to make sure, you can assume that we are sure that since the breakdown is larger than 5, okay, let's assume it's 6, for example. Okay, you can put it 6, for example. Okay, and assume that D1 in breakdown, so it must have minus 6 volts, rather than the discrepancy of having minus 6 as one of the elements of the circuit, and the input itself is only 5. Okay, you can continue and you will reach a conclusion that, you know, something is wrong, but do it yourself, and, you know, as exercise, not a homework, but you will find that this will be incorrect assumption. Okay, so let's do B now. So in A, V breakdown was larger than 5, so we were sure that D1 will not be a breakdown, only reverse, and we could solve it easily. And this is, by the way, exact solution without making, you know, any alternative solution or something. Now with B, if V breakdown is equal to 4.9, now V breakdown is less than V input, and it's exactly equal to 4.9. And now I know is given equal to 5 microamps. And the question is find I. This is I here. It's given with this, you know, polarity, this direction in the circuit. So we don't change it. Should stick to what's given. Okay. Now let's look at A first before going into B. At A, when V input is equal to 5, we found that VD1 is equal to this value here, 4.98. As a magnitude, this is larger than 4.9, right? You should say right, yeah, okay. And in B, V breakdown is 4.9. So it's reasonable now to assume that D1, which we know it's reverse, to assume it's reverse and the breakdown. And D1 is still forward. Okay, so in B, when V input is equal, if V input is still V breakdown now is equal to minus 4.9, we see that from A that VD1 is actually larger than a magnitude 4.9, so it's reasonable to assume that D2, D1 is in breakdown. Reverse and breakdown. D2 still forward. Forward means positive voltage, positive current. That's it. I don't know much. Good. So let's continue on that and see what will happen afterwards. So since we assume that D1 is breakdown, so VD1 is equal to minus 4.9 volt. Remember, the required is I, this current here. From Kirchhoff voltage law, V input plus VD1 minus VD2 equal to 0. V input is actually 5 volts. VD1 is minus 4.9 minus VD2 equal to 0. So VD2 from here will be equal to how much? Equal to 0.1 volt. 0.1 volt. Okay. Okay, so ID2 can be calculated. It's equal to I naught, which is known because it's given here in B. Yeah, 5 microamps. This is 5 microamps. Exponential VD2, which is known 0.1 over 26 millivolt minus 1. So from this we can calculate ID2. It will be equal to how much? Equal to what? Yeah, 228 microamps. Now let's go to the circuit. I actually is equal to ID2 because they are in the same branch and also same direction, same polarity. So this is equal to I. I check here. We said that D1 is reverse and the breakdown. And based on that, we assume that we conclude that VD1 is equal to minus 4.9. Okay, let's look at the characteristics. ID1 must be negative, and as a magnitude must be larger than minus I naught. Right? We know that ID1 is equal to minus ID2. In that case, it will be minus 228 microamps. It's a negative. That's very fine. How about the other condition? It must be larger than minus I naught, at least minus I naught. Okay, that's the beginning, just at the beginning here. I naught is actually 5 microamps, so ID1 as a magnitude, which is 228, is actually larger than 5 microamps, much larger than. The second check here. Okay, so this is how to check on yourself. If you assume that D1 is not, I did it myself here. If you assume that D1 is not breakdown, you will find some discrepancy in the outputs that you get. then you know you will go back and it's a breakdown. So let's do that, and you will find the correct solution. So again, it's like a game, okay, based on common sense, the givens that you have, the intuition, you assume something that you believe it's correct, and you prove or disprove it. If you disprove, then go back and assume another assumption and take the disprovement in your account. So if you assume that it's not a breakdown, for example, then okay. So if it's not a breakdown, so what else? So it should be a breakdown. So you know, that you have only two directions. So if one of them is incorrect, so the other should be correct. Okay, guys, we have 2 minutes. I don't know if you have time or not, but that's very fine for today. Okay, we're gonna continue next time with diode. Now, next time, so far, we are calculating the unknowns in the circuit, okay, accurately, either by solving the equations or by something based on common sense. Okay, next time we will see a more easy way, actually the easiest way to deal with diodes in circuits, which is models. And based on these models, we will solve even much faster than what we are doing right now. Just one quick note on that example in particular before we go away is about ID2, which is the current of the forward bias diode. We found that, okay, let's draw very quick here. Just we go back to this analogy again, okay? So this is VD2, ID2. We know that this guy here, this voltage should be approximately equal to 0.7 volt, or between 600 or 700 to 800 millivolts. That's fine. Around 700 millivolts or 0.7 volts. Then you know that if the voltage is 0.7 or something higher, the current should be much high. Okay. But since this guy here is connected with another reverse bias diode, so they are restricted by this reverse bias diode, and the current is small, okay, equal to only I naught, which is in B was just 5 microamps. So we are expecting that we should work somewhere in that region here before the voltage become 0.7. And that's what actually happens. We found that VD2 is equal to 0.18 millivolt. Very, very, very small. Something maybe here or something. Very small. Much lower than VD2. And this is again happened in that case here. Okay? Because the input is only 5 volt. 4.9 of them goes to D1 and only 0.1 goes to D2. We still far away from VD2 0.7 volt. So again, the current was very small. It's in microamps. Only 200 microamps. In particular for that diode, if you go to 0.7 or beyond, you will find probably the current in milliamps, okay, very high, or maybe amps. Okay, so that concludes this today's lecture. Thank you guys very much. We see you tomorrow in the lab. Okay, thank you.